So we have obtained this metric on anti-de Sitter space, which covers entire space-time, hyperbolic cosine of rho d tau squared minus d rho squared minus hyperbolic sine of rho d omega d minus 1, d minus 2 squared. Notice that d minus 2 coordinates here, one here and one here, so it's d-dimensional space-time. And now we want to draw a Penrose-Carter diagram on this space. So we're going to make the following change. And we want to tangents of theta will be equal to hyperbolic sine of rho. So hyperbolic sine of rho we change for the tangents. And as a result, this metric acquires, after this change here, we get the following metric: h squared times cosine squared of theta times d tau squared minus d theta squared minus sine squared of theta d omega d minus 2 squared. So now one also has to consider, you see the range of validity again. For d equals to 2, rho is ranging from minus infinity to plus infinity, and for d greater than 2, rho is ranging from 0 to plus infinity. That, of course, imposes a difference that in case of d equals 2. So as a result, if we have d equals 2, then theta is ranging from minus pi over 2 to pi over 2. And for d equals to greater than 2, theta is ranging from 0 to pi over 2. And we have two different situations. So for d equals 2, Penrose diagram following from here is exactly the same one as we had in case of a de Sitter space, which is just this rectangle, but it's like rotated by an angle of p over 2. So this is a timeline, tau. Remember that in our case, tau, these two sides are glued to each other, and if we consider universal cover, it just becomes a stripe for tau ranging from minus infinity to plus infinity. And theta is ranging from minus pi over 2 to pi over 2. In our case, like tau is ranging from 0 to 2 pi, or from minus pi to pi. Well, anyway, so this, for the appropriate anti-de Sitter metric, tau is compact, and this is exactly what we have. And the fact that time is compact leads to the fact that this is a cylinder. So that's the same cylinder as we had for de Sitter space, but just rotated by the angle pi over 2 along this axis perpendicular to this plane. That's what we have for two-dimensional case. For this case, for the greater than 2 dimensions, if we use this spot, we have the following situation. We have the following situation that, let me draw it like this. So along theta, we have from 0 to pi over 2. And this is straight. And here we have from 0 to 2 pi. So this is 4 times longer than this. And it is important that here, in 2 dimensions, these are 2 boundaries of the de Sitter space, anti-de Sitter space, and this corresponds to rho equals to 0, and this corresponds to rho equals plus infinity. This is not boundary, this is the center of the disk, while this is a boundary of the anti-de Sitter space. And again, if we are dealing with appropriate the range of values of tau, then this is glued to this. If we deal with universal cover, this becomes a stripe. And now we encounter a very interesting situation for this case. Notice that light rays again are just straight 45 angle degrees with respect to this. And we have the following situation. Well, actually, it 4 times. This side is 4 times longer than this side. So my picture is not quite appropriate. But it's important that from any point inside de Sitter space, light rays reach the boundary, spatial boundary, within finite proper time. And actually, the particles are, massive particles go along these lines. So anti-de Sitter geometry acts so it attracts back massive particles, and for light rays it acts as a box. So we have kind of like as if at a finite distance along this direction. So it acts as a box. And this leads to some peculiar property of the anti-de Sitter space. Like if we solve Cauchy problem in space-time, we have to solve kind of causal equations, causal differential equation. Then if we want to specify a behavior at some point O, we have to consider a causal path of this point. So we go to the backward light cone, and to obtain something here, everything depends on the values inside this light cone only, not on something here, because we are dealing with causal situation. So if we specify initial conditions at Cauchy surface, then it gives us the value of the field or solution of differential equation at this point. That's what happens in, say, in Minkowski space or in de Sitter space or in other regular spaces that we have encountered, Schwarzschild, etc. But here we encounter a new feature that the boundary of the space is reached within finite time. So this is, well, our space-time acts, its spatial sections are like boxes. And the Cauchy problem is if you specify initial value at Cauchy surface, it doesn't give you the value of the field here, the value of solution of the differential equation here. You have to also specify boundary conditions on top of the initial conditions. And this feature, this property of anti-de Sitter space is called as absence of global hyperbolicity. It's just because related to this fact that you can reach within finite time. So if you want to solve something here, you have to specify boundary conditions here. Well, boundary condition here, better to say, because this is not a boundary. Boundary condition here and initial condition here. This is absence of global hyperbolicity of anti-de Sitter space. That's how it reveals itself. And we're going to continue our discussion with Poincare coordinates and Poincare patch of anti-de Sitter space.